Okay, welcome back, everyone. All right, 2 more lectures left in the entire class. I think everybody saw there was a correction on homework 6, so I apologize for any wasted hours trying to solve an unsolvable problem. But it should be simpler now. I'm really glad this wasn't a final. It was just a take-home homework. Okay, so today we're going to continue talking about the singular value decomposition, and we're going to look more at how to do essentially curve fitting and looking at high-dimensional data sets with the singular value decomposition. And then on Friday, the final lecture, we're going to build a machine learning image classification software in our computer. So we're going to train our computer how to tell the difference between 2 people using the singular value decomposition. Any questions about the SVD from last lecture or anything that we've talked about so far? Nope. Okay, good. So one of the things we're going to do now is talk about the pseudo inverse and least squares solutions to matrix systems of equations. Okay, so SVD and the pseudo inverse. Okay, so let's say that I have a matrix system of equations like AX equals B. Okay, we see these all the time in linear algebra. We have some matrix A that we know. We have some vector B of measurements that we know, and we want to solve for X, the unknowns. And this could be a system of equations to determine the forces in every element of a bridge truss, for example, or lots and lots of other examples. A could be a discretized Laplacian. B could be some forcing. And X would be the vector potential. Okay. So if A is a square matrix, which means that I have as many measurements as I have unknowns, then you can just invert A and solve for X, as long as A is invertible, right? As long as its determinant is non-zero. But what if A is not a square matrix? What if A is either a tall, skinny matrix, or A is a short, squat matrix? Then what are our options? Okay, pseudo inverse, yeah. So let's take the first example where I have, I like drawing these with actual shapes because it helps me think about what's happening. So let's say that I have a tall, skinny A matrix, which means that my X vector has to be small. It has to be the width of A. So X is kind of a short vector of unknowns. And this equals a really, really tall vector of measurements B. So what can you say, generally speaking, about the solutions X to the system of equations? Are there going to be solutions? Is there one solution? Are there many solutions? What can you say about what's likely to happen with this, this solution X? Okay, so we call this overdetermined, meaning I have way too many measurements. And typically, there is no solution X that satisfies all of these equations simultaneously, right? Every row of this is an equation, and I have way more equations than unknowns, and it's very likely that some of these equations will conflict with each other, and they'll just be fighting, and you can't find an X that satisfies both of them simultaneously. So in general, we're unlikely to have a solution to X. In what cases might I have a unique solution to X for this system of equations? The rank of A is low, which means that a lot of rows of A and B are linearly dependent. So if I had a lot of duplicate rows of A and B, that would be fine. Or if I had, combinations of earlier rows down here and combinations of earlier Bs down here, that would also be fine. And then maybe my multiple rows of A aren't fighting with each other, and I'll have a unique solution. That's possible. But if I just randomly sample a big A matrix, if I just fill it with rands, and I fill B with rands, there's basically no chance I'll ever find a unique solution X. Okay? Okay, so this is case 1. And case 2 is the other example, the short squat case of A, where I have a super tall row vector, column vector X, really squat A, and now my measurement vector has to be short. So in general, what can I say about the solution X for this system of equations? Okay, lots more unknowns than there are equations, so we call this underdetermined. There's not enough information to determine the solution. And what do we say about this underdetermined system? What's likely? So let's say I randomly populate A with values and I randomly populate B with values. What's likely to be true of X? Yeah, so I'll definitely be able to find at least one solution. There should be a solution because if I randomly make A, it's very unlikely that the rows will be linearly dependent. So there will definitely be at least one X, but it's actually likely that there will be infinitely many X's, right? I have all of these degrees of freedom in X that have no bearing on the relationship between A and B. So it's very likely that I'll have infinitely many X's. Now, what are some counterexamples? What would be a case where I would have no solutions to X? These are just general guidelines. They're not always true. Sometimes I'll have infinitely many solutions to an overdetermined system. Sometimes I'll have no solutions to an underdetermined system. When might I have no solutions to the system? Okay, let's say that I do an example, and I have X is the ages of Jack, Ben, and Molly. And let's say that Jack's age plus Ben's age plus Molly's age equals 55. And let's then say that Jack's age, 2 Jack's age plus 2 Ben's age plus 2 Molly's age equals 20. Right, so I have linearly dependent rows of A, and I have completely inconsistent measurements of B. So I could cook up a stupid example where I just make this break. There's no solutions to this underdetermined system. Okay? And you can have similar examples here where I just take the same row equation and I repeat a bajillion times and I have infinitely many solutions. That's totally fine too. Okay, so these are just general guidelines of what might happen in these cases. So this is all we're doing now is talking about what types of solutions there will be. But I haven't told you how to solve it. How would I actually, okay, so this is a bad example. How would I actually solve for the X in either of these two examples? If A was square, we would just invert A. Okay, so let's take the singular value decomposition of A. Let's write A equals U sigma V star. So in the case of a tall, skinny A, we have A equals, now U is big square matrix. Sigma is the same size as A. And V star is a little square matrix, the width of A. Okay? So I have A is the product of these three matrices. And we have AX equals B. So what I can start doing is I can start inverting each of these pieces. Okay? I can start inverting each of these pieces, and I can essentially say that X is approximately equal. So the first thing I'm going to do is invert U. And what's the inverse of U? U transpose. Okay, so I have, let's just write this out. We have U sigma V star X equals B. And so I'm just going to left multiply by U star, and I get sigma V star X is about equal to, I'm going to write approximates because there's some things that are happening here, u star b. So I multiply both sides by u star, and I get an identity here. Okay, then I can multiply both sides by sigma inverse. Now, sigma is not a square matrix, so I'll tell you what sigma inverse means in a minute. So I get v star x sigma inverse u star b. And then finally, this v star is a square matrix. The inverse is just v. And so x is about equal to v sigma inverse u star b. Okay, and so this thing is called the pseudo inverse of A. It looks like the singular value of decomposition of A, where everything is flipped and transposed and inverted. Okay, so I glossed over a super important step here. How do I invert sigma? I can't really invert sigma, right? Okay, so there's a really important thing that is happening here. So this A is really equal to, I'm going to call this UR, where R is the rank of A, how many linearly dependent rows and columns A has, followed by some other stuff. I'm going to say it's perpendicular, and I don't care about it. And then I'm going to have some square matrix, sigma R, an R by R square matrix, and zeros everywhere else. And then I'm going to have VR star. Let's say that this A has full column rank. So the number of columns is equal to R. So basically what I can do is I say that I can break this U into the first part that multiplies my non-zero singular values times my non-zero right singular vectors V. And then everything else is multiplied by this big zero matrix. So this equals UR sigma R VR star. A is exactly equal to just these first R columns times the first R by R singular values times the first R by R singular vectors, V. Does this make sense? Right? You have this big zero chunk in the middle of sigma, and so everything that multiplies that is just cancels out. Okay, good. And so really all of these have R's in them. Okay, and now this sigma R really is a square matrix that I can invert. So every step here is fine. This U R transpose, this U R is not a square matrix, but I can still take the transpose and I can still multiply it by B. And I can still take the transpose and I can multiply it on the left of UR, and I still get an R by R identity because the first R columns are orthogonal to each other. Okay, so anyway, this is how I do the pseudo inverse. This is really, really, really important. This is the pseudo inverse. And the great thing is that it actually solves for X for every single possible combination that I've told you about. It solves for the overdetermined case where I have one solution or no solutions or infinitely many solutions. It also solves in the underdetermined case where I have no solutions, one solution, or infinitely many solutions. So regardless of how many solutions X has, regardless of the shape of A, I can always do this pseudo inverse and get something that approximates this X that approximates the best X for this matrix system of equations. So I'm going to tell you what I mean by best X now. Questions about this before I go on? A little bit hairy math. You should really write these things out. In the pages that I've included for the lecture notes, I actually have pictures really illustrating exactly what the shapes of these are. Yeah?
What if A is not a full rank matrix?
If A is not a full rank matrix, then you still have the first R columns. So R would be the rank of A. And then I would really have something that's like this. I would have sigma R with some zeros. There would be some zeros to the right and below. And then I would have V R star and then V everything else star. So I would also break V into its first R columns and throw away everything else. So in general, if the rank of, so A, it might have rank 1, and then it would be 1 column, 1 number, 1 column, transposed, makes it 1 row. So this is super, super powerful. If I have a non-square matrix, I can approximate its inverse or something like its inverse. It's a pseudo inverse. And I can solve matrix systems of equations that might have no solutions, infinitely many solutions, or 1 solution. And the solution that I get is what's called an optimal solution. It's optimal in the sense that it either minimizes the error between AX and B, or it minimizes the length of the vector x that you get out. Okay? So how do we say this? If there are no solutions, if there are no exact solutions, to AX equals B. And remember, I can have cases where there's no exact solutions to this for both overdetermined and underdetermined, but it's much more likely for overdetermined systems not to have a solution. Then X approximately equal to VR sigma R inverse UR transpose B minimizes the norm error. So it minimizes AX minus B, which is just a vector of the same length as B. It minimizes the 2 norm of that vector. And what is the 2 norm of an error vector? It's just the sum of the squares of all the terms. So it's the mean square error. So this minimizes, this is called a least squares solution. Because it minimizes the mean squared error. So in that example where I had my matrix 1, 1, 1, 2, 2, 2 times x equals 55 and 20, where this was totally inconsistent, I can find the best possible x that gets the closest to satisfying both of these rows. Right? Like I'm going to have some x, and it's going to do the best it possibly can at satisfying both of these rows. And that solution with the pseudo inverse gives me the single best possible x that minimizes the error of this system of equations that are inconsistent. Okay, so if I have noisy data, my noisy data might be like there's not an exact x that'll fit my noisy data because the noise is confounding everything, but I can find the best x that minimizes the error between all of my measurements. Okay, so this is a least squared or minimum error norm. In the other case, so this is again kind of case 1. In the other case, let's say if infinitely many solutions, and there's usually infinitely many solutions if I have a massively underdetermined system, so a really short, fat A matrix, really, really tall X, and a few measurements B. So if I have infinitely many solutions to AX equals B, then the pseudo-inverse solution, and I'm just going to, there's a symbol for this. We say X equals A dagger, not the transpose, it's a dagger. It's awesome. So X equals A dagger B, the pseudo-inverse of A times B, minimizes the length of X, which is the 2 norm of X. So the length of any vector, right? The length of a 3 vector is the square root of x squared plus y squared plus z squared. That's what this 2 norm does. It minimizes the length of my vector x. And so this is called a minimum norm solution. So even if there's infinitely many possible x's that solve my system of equations, this might be the best one because it's kind of the shortest, it's the least effort x that gets me a solution. It's the least number of values. Maybe this system of equations is a times x equals b, and maybe x is a history of how I can spend gas to get from here to California, and there's lots of different ways I can accelerate, so there's a ton of possible x's. And the minimum norm x would be the most fuel economic way of getting to California. So a short x is often a really good thing. Short x means a lot like less energy spent sometimes. So the pseudo inverse is incredibly powerful. Oftentimes we have systems of equations ax equals b where there's either no exact solutions because there's noise. There might be plus noise. Or there might be infinitely many solutions because I don't have enough measurements. And in either case, the pseudo inverse is giving me an optimal solution in a way that makes physical sense. It's either minimizing the error or it's minimizing the norm of x. Okay, so let's do a really concrete example here. So the simplest example is the following. Okay. Okay, so let's say that A and B, just going to make this lowercase because these are scalars. Let's say that A and B are my axes, and I collect a lot of data, a lot of noisy data. Okay. You could say that A is time in years, and B is tree ring diameter in, doesn't matter what units, meters. Okay? So for example, I can collect a ton of data. I can go, unfortunately, I might have to chop down a lot of trees to get all this data, but I can go sample a forest and I can measure how many rings it has. So A was like number of rings or number of years, and B would be the diameter of the tree. How big is it? And there should be a pretty strong correlation between the age of the tree and the size of the tree, the width of it, right? So what I might want to do is find a model, AX equals B, where X relates the age of the tree to the width of the tree. And I want to find the best slope, X, to this line. Make sense? So I have a bunch of pairs of points, A1, B1, A2, B2, A3, B3, A4, B4, et cetera, et cetera. And I can stack these as a big matrix A times a single number x. This is like the most degenerate case, equals a big vector B. And I want to find the single best possible value x that matches all of this data as well as possible. And of course, there is no x that exactly solves all this data, right? Because there's error in almost every single one of these points. But I'm going to find the x that minimizes the error of this line to the entire fit. Make sense? This is how we use the SVD. One of the main ways that we use the SVD is for things like this. You could do this in multiple dimensions. If there were other factors, A2 and A3 and A4, like maybe it wasn't just time, but it was annual rainfall and sun activity. You could have all of these factors that might correlate even better with tree diameter. And you could do the exact same thing with the singular value decomposition. Okay, questions about the problem formulation before we code it up? Yeah.
If you have many factors that you're considering, that increases the dimensionality of the problem. So would you...
So let's say that I had multiple factors, like not just age, but I also had time. Then I could have A1 column, which is time, and A2 column, which is rainfall. And then I would have X1 and X2. And I would still be solving a massively underdetermined system. There would still be error in every row. but now I have two unknowns. How do these, how does the tree ring diameter jointly relate to both annual, like number of inches of rain and the tree age? Okay? And I could add as many factors as I want, and I could try to get a better and better and better model. And at some point, I might even have more factors than I have measurements, and then it becomes a minimum norm solution. I want to find the most important factors. Okay? Good question. All right, so this is the basic formulation. I have a slope 3. I've just made this slope up. I'm going to cook up some data A from -2 to 2 in increments of 0.25, and I'm going to transpose it to make it a big column vector. Then I'm going to take B equals AX plus some noise, a lot of noise, 1 times rand n. And I'm going to plot that against also the true solution. Okay, so let's put in a legend here. Legend, what is this? True, slope, and noisy data. And this is what my data looks like. Okay, makes sense? So the X line is my truth data. This is the underlying fundamental truth of the data that I've cooked up. And then I have Gaussian noise on top of this. And what we're going to do is we're going to act like we don't know what this black line is. We're only going to look at the red points, and we're going to try to make our new blue line, which is the least squared solution. Okay, and the way we're going to do it is the following. We're going to take the SVD of A. Super simple. I'm doing what's called an economy SVD, because if you ever do the SVD on a really asymmetric matrix, a really tall or a really wide matrix, then you should do economy because it's faster. And then I'm going to say that X tilde, my least square solution for X, is V times the inverse of S times U transpose B. And the economy is nice. It's only going to give me the columns that I want. Remember how we broke it down into UR, sigma R, VR star? The economy SVD is going to do that for me. It's going to throw away all of the no rank stuff. Okay, good. So now I have U sigma and V, and the sizes are what we think they should be. They're just all, U is a single column vector, V is just a number, and sigma is just a number. Because this is a rank 1 system. A is a single column. Okay, and now if I want to plot what my best model fit for the system is, it's just X tilde times A. It's just all of this stuff times A is my best model fit for the tree ring data. Should probably run it all at once. And you can see it's not perfect, but if you didn't have the black line at all, this blue line would be better than nothing, right? Okay, how would I make my fit better? Increase the number of measurements. What's another way? Sorry?
Don't hold it to a linear line.
But let's say that I really think that this is a linear line. So I could overfit, actually. I could make a quadratic line. I could make a 20th order polynomial that hits every single one of these points, right? I could overfit. That's a really tricky issue. Let's just say that I increase the number of points. So instead of 0.25, I go down to 0.1, and I run the same thing again. With 2.5 times more data, now my blue and my black lines are almost on top of each other. So essentially, we're averaging out all of this noise with the singular value decomposition. We're filtering our solution, and we're getting a better and better fit the more data we have. Okay, make sense? Now in MATLAB, there's a nice, easy built-in command called pinv. So you don't ever have to type in V times invest times U transpose. You could just type pinv of A, probably. That should work. That also works. But I just wanted to show you that this really is exactly the same as the pseudo inverse. There's another way I could do A\B. That also works, I think. Sure, that works too. So lots of ways to do this in MATLAB. Okay, questions about this simple example before we go on to something more sophisticated? No? Okay, good. So now what we're going to look at is cancer data. Actually, maybe I should do... I might only have time to do the cancer data. Okay, I'll do cancer data first, and then I'll come back to the very exciting world of cement mixing. It's one of the funner examples we have. It really is actually quite interesting. Okay, so let's do the ovarian cancer data set. So what we're going to look at is the following. Now I can't remember the exact size of everything, because these are built-in data sets in MATLAB. So MATLAB has a lot of great built-in data sets. You can Google MATLAB built-in data sets, and you'll find a list of about 20 of them. So they have the classic CARS data set, ovarian cancer, ionosphere measurements, cement mixtures, like all of these classical data sets where you can try out these methods on them. And so the ovarian cancer data set is an example of how we use this SVD for principal components analysis, PCA. And nowadays, the SVD and the PCA, in my mind, are kind of synonymous. They do the same basic thing. But PCA goes way back over 100 years. This is a statistical method to find the correlations in high-dimensional data. Okay, so the example I gave you as tree rings is actually not too far off. There would be an example where they would go look at clams, and they would measure every dimension of the clam, the mass, the length, the height, the width, the size of the tongue, like all of, they'd measure 10 things, and they would also have some proxy measure for age. In some cases, they would actually know this, and they would try to build a model from those factors to the age. Okay, and principal components analysis is one of the ways you do that. Basically, the principal components analysis takes a big data matrix X, and it tries to find the dominant correlations in X, just like the SVD does. So if I take the SVD of X, I get the principal components analysis. But usually what I do is I subtract out the mean of X first, and I divide by the variance of every row. So let me give you an example. Differences, the major differences between SVD and PCA. So I told you that in X, I stack my measurements as big columns. Right? So for example, if I sampled the blood from everyone in this room, which would be creepy, I could find what your gene expression were for like 4,000 genes, and I would have a 4,000 by 50 matrix. Okay? In principal components analysis, we would stack those measurements as rows. So like the big measurements that correspond to one individual, those are now rows. So now my X is going to look like my measurement 1. This is all of the genes for person 1, all of the genes for person 2, up to all of the genes for person 50. So this would be like a 50 by 40,000 matrix. Super simple difference. All I'm doing is transposing it. Okay? And so my singular value decomposition in this case, X equals U sigma V star. Now the things I care about, the correlations between gene expression, are now coded up in the columns of V, which are the rows of V star. Okay, so rows of V star play the same role in PCA as columns of U before. So it's just a total, I mean, it's like if you went to a different country and they buttered their toast butter side down. Okay, it's exactly the same, except they transpose their matrix first. Make sense? Nothing else changes. These guys got here first also. So we're the dissenters. Okay, and usually we would subtract out the mean, and we would divide by the variance of each row so that they were all kind of unit variance. So maybe if one person just had more gene expression everywhere across the board, I would bring us all down to the same level. Okay? Because I want to look at the relative differences between gene 1 and gene 50, et cetera, and I want an apples-to-apples comparison. So maybe you just have more gene expression than I do on this day for some reason. Maybe you had a breakfast and I didn't. Okay? I did eat breakfast. All right, so this is what our data is going to look like. And then what we're going to have is essentially, for every person, we're going to have a label of whether they do or do not have ovarian cancer. It would make sense if these were all women, but they might not be. I don't know. So I would have labels for all of these people about if there is or is not ovarian cancer, and then I can essentially look at the gene expressions for each of these people. So what I want to do is I want to look at the 3 most dominant modes. And what are my modes that I'm talking about? Eigenvectors of x star x. So they're either columns of U or columns of V, depending on how I stack my data. So the 3 most dominant modes, I think in this case they're 3 first columns of V. And then I want to look at how each of the people, what their expression is in those columns. So in MATLAB, I can take V colon, the entire column of V, 1 to 3, the whole first 3 columns of V. And let's just say that these are columns of U, because I know how to do this for you. Let's say that I have columns of U and I stack my data like a normal person. I could take that transpose times x, and what I would get are coefficients. I would get 3 numbers for each person. So for U, I would get your alpha 1, alpha 2, alpha 3, which tells me how much of modes 1, 2, and 3 you have, versus U and U and U. We would all have our own alpha 1, 2, and 3 mixture. And maybe people with ovarian cancer have a fundamentally different alpha mixture than people without ovarian cancer. That's the hypothesis. Okay? Okay, questions before I code this up? Standard deviation. Taking the STD before taking the SVD. Might be the variance. I don't know. It shouldn't matter a lot. Okay? Well, because I'm trying to make this thing unit variance, which would also have unit standard deviation, so it shouldn't matter. Okay? All right, let's just jump in then. I honestly can't remember in my data set if I stack it like PCA or like SVD, so we'll find out. Okay, so I told you that some of these are built into MATLAB, which is great. So ovarian cancer is just already pre-built into MATLAB. You can just say load ovarian cancer. And what I get are a big matrix called observations, and this is 216 by 4,000. So this is the PCA way of stacking things. I have 216 patients, 4,000 genes per patient. They're stacked in rows. Okay, all of the genes are stacked in rows. And group is a set of labels which tells me which group they belong to. So let's just look at group. If I just type in group, I have a bunch of normal and a bunch of cancer. So I have labels for every single patient. So the first 113 might be in the cancer group, and the other ones are in the normal group. And so I can color these different patients based on their category. It's a really nice data set. This is real data. Okay, so I take the SVD, and what am I going to do? So I take the SVD, it takes a while. And now what I'm going to look at are what are my distributions of singular values. Right? So I always want to look at the diagonal elements of sigma to see how dominant are the first modes that I'm going to be using, how important are they. And I see that my first mode captures about 55% of the variance in the data set. That's great. That means everyone in this room shares about 55% of the same mixture describes all of the data. And then, or different levels of that first mode will explain the differences in all of our data. And then the next mode picks up another 6 or 7%, then another couple percent. And the cumulative variance of the first three modes is about 64%, which is good. That's actually really not bad. That means I can explain a lot of the variance in our data just from the first three modes. It would be kind of disappointing if these were way down in the 5 or 10%. That would mean that there's a lot of stuff that we're not getting with the first few modes. Okay, now what I'm going to do is for every single patient, for every row of observation, I'm going to multiply it by the corresponding column, the first column of V, the second column of V, and the third column of V. So I'm going to get the alpha 1, alpha 2, alpha 3 coefficients for every single person in my deck, in my observation deck. And if they're the cancer group, I'm going to make a red X. And if they're the healthy non-cancer group, I'm going to make a blue circle. Okay. I should probably label X. Let's try an X label. This is PCA1. Y label is PCA2. Z label is PCA3. And do I have, should probably put a legend on too. It's very likely that the legend's going to bomb out. So cancer is red. And you see here that there's actually a beautiful separation. I mean, it's not perfect in the first three modes, but I clearly have clusters of cancer and not cancer. And you could even imagine that there's a pretty darn good line I could draw through these where I might get 80% diagnostic capability, right? So if you come into the doctor's office, they run a simple test. They take the dot product of your gene expression with PCA modes 1, 2, and 3. And then if you're way over in the center of the blue region, you probably are okay. And if you're way over in the center of the red region, they should probably do more tests for cancer because it's likely that you have ovarian cancer. Okay? Super fast, cheap, pretty good diagnostics based on principal components analysis. Now, how would I do a better separation between these two categories? Increase the number of modes. So if I look at just PCA 2 and 3, that's actually, there's more mixing between them. Right? And when I look at just PCA 1 and 3, there's also a lot of mixing. But when I get all of the modes together, that's when I start seeing a pretty clean separation. And so maybe if I had PCA 4, 5, and 6, they would actually really separate a lot more in those dimensions. Maybe I would really be able to draw a line and get 99% categorization. And it turns out that you can do exceedingly well at telling diseases apart just from these low-dimensional representation of gene expressions and things like that. What other things could I do to make this better? What other analyses could I use to make this data better? Yeah, so I could try to apply machine learning to these three numbers, to my alpha numbers, and I could try to find better ways of separating them. I could also add more data. I could add demographic data. I could say, well, what is the age, race, and diet of these people, right? There are biases in cancer based on age, race, and diet, and other habits like smoking, non-smoking, things like that. Like maybe your gene expressions are different because you're a vegan. Maybe your gene expressions are different because you only eat meat, right? Maybe gene expressions are different because you're a smoker. Maybe a lot of this variance can be explained by metadata that would actually bring these a lot more into clusters that would be, okay, well, I have my carnivorous normal and my carnivorous cancer and my smoking, under 35 normal and my smoking under 35 cancer, and I could add more data that would give me more features to separate. Yeah.
In the original data set, would they go on the end of the gene expression?
So there's a few ways you could do it. I could tack on metadata, and I could even weight it more heavily in my X matrix. That's one way to do it. That's not how I would do it. I mean, I would just do a hierarchical classification where I would color these things now instead of X's that are red and circles that are blue. I might have, maybe smokers and non-smokers are the circles and the X's. And maybe normal and cancer are blue and red. So now I have 4 types of markers. And whenever I get a diagnostic for a person, I first ask you the metadata, and that trickles down this tree, and I look at a much more restricted set of people's gene expressions, and I get a much better idea of is your gene expression normal for your type of demographics, for your metadata. So there's lots and lots and lots of ways to do this. I could also feed that into the machine learning algorithm. So what I give the machine learning algorithm is alpha 1, alpha 2, alpha 3, age, race, gender, and all of the metadata. So I could augment my features with that metadata. There's whole classes on this type of dimensionality reduction, and there's whole classes on this type of machine learning. There are dozens, hundreds of methods to learn from this data how to best classify things. Like, this could be people that will pay money in a video game and people who won't. Right? Like, let's say you're playing some phone game and they want to get you to spend 99 cents a bunch of times. There are people that will pay easily and often, and there are people who will never pay no matter how painful it is. And you might want to machine learn those people. And I might even want to force these people into the paying category if I have some control mechanism. Okay, I might want to manipulate people. That's how Amazon and Walmart and everyone who makes money works. Okay, they break people into demographics based on features. These used to be determined by experts, right? A bunch of people would get in a room, and experts would say, okay, well, you have different categories of people, and those different categories like whiskey and cigars, and other categories like, different things, and then they would target the advertising and the purchasing to the different people based on expert knowledge. This is just a way of mining that knowledge from existing data. Okay? Tons of stuff you can do with this. It's really limitless. There are limits, there's big limits, but there are a ton of opportunities for this type of data analysis. So the last example I'll show you on Friday is how to use this kind of dimensionality reduction to take very, very, very high dimensional data like genes or like all of the pixels in a megapixel image of a face and actually build one of these machine learning setups to tell the difference between 2 different types of people. So it's the last example. We'll do kind of our Facebook eigenfaces example. Okay, thank you.